Good morning, everyone. Today we are going to explore phase one of the Computer Vision course titled Foundations of Image Processing and Visual Data. This phase is the entry point to a fascinating discipline where computers learn to see, interpret, and act upon visual information. Our main objective in this phase is not only to study the theory, but also to connect research, practice, and real-world application. To guide your learning, we will rely on four key references by book section. The first one, Amaya Sandino, 2014. It's titled Preliminary Method for Detecting Pathogens in Strawberry Crops Using Digital Imaging Processing. This article illustrates how classical image processing techniques such as filtering, color conversion, morphological operation, and cartoon analysis can be applied to agriculture. It demonstrates that non-destructive image-based monitoring is a practical solution to detect diseases like Botrytis sp and Spirotheca sp, early reducing crop losses. From this study, we will learn the importance of preprocessing to reduce noise, segmentation to isolate regions of interest, and feed restriction for diagnosis. This is the article. As I say, this research focuses on non-destructive detection of biological patterns in Blackgaria and Anasa strawberries, particularly Botrytis gray mold and Spirotheca powdery mildew. Traditional methods often require removing fruits from the plants, analyzing them in a laboratory. It's obviously time-consuming, destructive, and impractical for large-scale monitoring. Amaya and Sandino propose a digital imaging processing algorithm that works directly on image capturing the field and simple 16 MP digital camera under controlled lighting conditions. Some key processing steps. First one is image acquisition. Photos of the strawberry plants were taken directly in the crop without removing fruits. Conditions, daylight, 10 to 11 a.m., partially cloudy skies, avoiding shadows, stored in the GPS format. This creates a realistic dataset reflecting actual agricultural monitoring conditions. Color space conversion, images from the camera in RGB format were converted to SAV. Hue, saturation value. This step improved the distinction of breadfruit tones and made threshold holding more robust against lighting variations. Masking and thresholding, a binary mask was created using range thresholds in the HSV domain. This allowed the system to check whether the image actually contained strawberry fruits, detecting red tones. If no fruits were detected, the algorithm aborted analysis. Number 4 is preprocessing and noise reduction. A media filter, smooth median, was applied to reduce random noise from the digital camera. Morphological operations, erosion, dilation, were used to clean the binary imaging and highlighting relevant structures. Segmentation and contour detection, the algorithm detected contours using OpenCV, 5 contours. Contours were analyzed for shape and size compared against reference patterns and for both arthritis and sparaoperas lesions. Number 6 were feature extraction and pattern matching. Case were simplified using Rammer-Douglas figure algorithm to approximate contours into polygons. Pattern matching was performed with high U invariant moments and OpenCV match shapes. This allowed classification of whether the detected shape matched the disease signature. Decision and diagnosis: if the structured factors match stored pattern, the system diagnoses the presence of the arthritis of Spiraotheca. Results were displayed through a graphical user interface showing the processed image, contours, and classification outcomes. What it says about performance and results. The processing speed: the algorithm achieved processing times around 70 to 24 milliseconds per image, fast enough for video analysis at 30 frames per second. Efficiency: tested with 15 images per pathogen, the algorithm correctly identified most cases, providing reliable data with monitoring tool. Deployment: the system was designed in C++ with some particular libraries of OpenCV, showing portability to PCs and even drones for aerial monitoring. What we can say about the practical contributions to the paper. Can use this. Non-destructive monitoring. Farmers no longer need to remove fluids for laboratory analysis. Monitoring can be done in the field. Cost-effective: uses regular digital cameras and open source tools. Scalable: can be embedded in mobile or drone-based IoT systems. Early detection: identifying pathogens before symptoms become severe, reduce product loss, and allows targeted intervention. The particular lesson for our cars from this paper, we learn several key lessons that are directly tied to our phase one objectives. Preprocessing, noise filtering, morphological operation is critical to prepare an image for analysis. Segmentations isolates the regions of interest, focusing analysis only on relevant cross areas. Feature extraction contours transform visual patterns into numerical descriptors. An application driving computer vision. The pilot is not just theory, it's deployed for agriculture, a real IT domain. The second reference. Open. This one. I'll talk about this one. This book, Embedded Vision, introduces us to the idea of vision system embedded into hardware, such as drones, robots, camera, and IoT devices. It shows how the combination of sensor, processor, and software brings computer vision into real environments. The perspective helps us to understand how an algorithm is not just code, it must run an optimized platform for real-time decisions. I don't have the full paper, I have the full book, but I'm trying to get it sooner or later. The third one is this one, Martínez TensorFlow 2.0. I got the book. This result moves into the modern area of deep learning. It covers image classification, transfer learning, segmentation, and object detection using convolution neural networks and advanced frameworks like TensorFlow. It demonstrates how deep learning extends to the capabilities of classical methods, allowing us to tackle complex problems such as autonomous driving, medical image diagnostics, and intelligence surveillance. This book is a practical guide that takes computer vision beyond classical methods in the modern age of deep learning. While traditional approaches focus on preprocessing, segmentation, and handcrafted feature extraction, Martínez showed how convolution neural networks on TensorFlow 2.0 revolutionize image analysis. The research is organized around recipes, short problem-focused implementations with ready-to-use code. Each recipe addresses a common computer vision challenge, making it highly practical for engineers and researchers. The key topics and techniques using in this book: image classification, building and training CNNs from scratch using TensorFlow and Keras APIs. Understanding the architecture, convolutional layers, pooling layers, fully connected layers. Example, I can say distinguishing between different categories of objects. For instance, cats versus dogs, healthy versus disease leads in crops, something like that. The transfer learning, using pre-training model like BGG 116, ResNet, Inception, and MobileNet, applying fine-tuning of feature extraction to adapt the system models to datasets. Benefits: faster training, better accuracy with limited data. Example, I can say adapted a pre-training model to detect industrial defects in factory production lines. Number 3 will be image segmentation, implementing semantic segmentation with architectures like UNet or fully convolutional networks, distinguishing between foreground versus background or different object regions in an image. I can say as an example is segmenting tumors in medical images or separating roads from pedestrian in autonomous driving systems. Object detection, applying region-based CNN, YOLO, and SSD, single shot detector for real-time detection. Object detection goes beyond classification. It localizes objects within bounding boxes. Example, we can say detecting multiple vehicles, pedestrian, and traffic signs simultaneously in self-driving cars. And the final one is TensorHub and model deployment. It has a lot of exercise. Leveraging TensorFlow Hub to quickly import and pre-training models. Exporting training models for deployment in mobile devices, IT platforms, or cloud services. Integration with TensorFlow Lite for edge computing, running vision models on smartphones or internet devices. What we have for real-time or real-life application, real-world applications. Martínez highlights how deep learning expands the frontier of computer vision, autonomous driving, real-time detection of cars, traffic lights, lanes, and pedestrians, medical imaging, segmentation of tumors, classification of X-rays, disease diagnosis, intelligent surveillance, detecting suspicious behavior, recognizing faces, or tracking moving objects, industrial automation, quality inspection, defect detection, and robotics, agriculture, land disease recognition, crop counting, and yield estimation with drone imagery. We can do some kind of comparison with classical models. The classical approach, as in Amaya Sandino, 2014, relies heavily on hand-printed features, color, shape, texture, requires manual parameter tuning, third self, works well with controlled scenarios, but struggles with variability, lighting, noisy, complex backgrounds. The deep learning approach, Martínez, this book, it learns features automatically from large data sets, generalizes better to diverse and noisy environments, scales to complex taxes, multi-class detection, segmentation of multiple objects, enables real-time performance on IoT and embedded platforms. What we can say about the lesson from the course, from this book, you will learn how CNNs from the backbone of computer, how CNNs form the backbone of modern computer vision, how transfer learning saves time and resources in IoT projects, how segmentation and object detection enable advanced applications like self-driving cars and smart farming, how TensorFlow 2.0 provides a robust open source framework for implementing, training, and deploying vision models. What we can say about the learning guide phase number 1. In this guide, we have 3 main products to develop on this phase. The first one is the concept map. Okay. After review the virtual, the literature and the references, you are going to deliver these ones. The concept map. This map must summarize the building blocks of image processing and computer vision, digital image, pixel resolution and color shades, RGB, HSV, grayscale, geometric transformations, rotation, scaling, and flipping, preprocessing, filters, normalization, and noise reduction, segmentation and feature extraction, thresholds, contours, descriptors, classification and deep learning, CNNs, transfer learning, IoT application, agriculture, security, healthcare, industrial automation, whatever you want. This map will help you visualize the connections between theory and applications. The second deliverable is this one. IoT workflow diagram. The guide asks you to represent the flow of information in an IoT-based computer vision pipeline. A standard sequence will be like acquisition, capturing image and video with cameras on sensor, preprocessing, cleaning and normalizing data to enhance quality, feature extraction, identifying meaningful patterns, age, shapes, textures, classification analysis using algorithms of deep learning models to interpret data, visualization or action, results can be shown in dashboard or trigger IoT actors, tuning on aggregation when a crude disease is detected. This diagram demonstrates how raw data becomes intelligent decision in IoT system. And the first and the last deliverable will be this, the analytical report, 500 to 700 words. The report is most important deliverable because it integrates the literature with your understanding. I suggest the following structure: introduction, explain why image processing is essential in computer vision. You can explain the classical foundation, what Amaya Sandino had said, show how image preprocessing and segmentation solve real problems such as pathogen detection. You can use the embedded vision by Vijayalakshmi, and you can use that to describe how vision algorithms live inside hardware, functional in IoT systems. And you can close with the modern deep learning by Martínez, highlighting how TensorFlow-based CNNs extend the capabilities of traditional methods, enabling object detection, segmentation, and intelligent classification. And you can close with the application in IoT, close with examples in agriculture, disease detection, security, smart cameras, healthcare, diagnostic imaging, and industrial autonomous robots for quality control. And finally, the conclusions reflect on how combining classical and modern approaches prepare us to design robust vision systems for IoT environments. what this phase is relevant, or what this phase matters. This phase is not only about producing the three deliverables, it is about understanding the evolution of computer vision from basic pixel level operation to AI driving the learning, from isolated algorithms to embedded systems running on IoT devices, from research articles in agriculture to modern industrial application. Each of you will begin to see how the foundation we will here become the tools you will use in more advanced phases and in real-world projects. So, as you work on your concept map, workflow diagram, and analytical report, remember that you are not only fulfilling an academic requirement, you are also building the skill set of computer vision engineer. Somewhere capable of connecting theory, software, and hardware to solve real problems in science and society. Thank you, and I look forward to see your work for phase number 1. Have you got any questions? Okay, that's all for me in this moment. We're going to start recording right now.